Okay, it's working. Good. So welcome to this second part of the class. In the first part we have talked about segmentation, and now we are going to talk about feature extraction and matching. We are going to talk about local and textual features. What I'm going to do is to present you one method, shift. Have you heard about shift before? Anything? Yeah, of course you do. I'm going to present you one only. There are many, but the idea behind is more or less the same. So I'm going to present you the most famous method, which is shift, and then you should be able to read other methods that are out there. But the idea behind is the same. It's finding points in images that can be matched with the same point in other versions of the image. This is the idea. And we also talk about texture features, which is a different thing here, or we'll see later. So this is the same slide that I put before. You missed the slide. But, this is, I put this myself, this is my own interpretation. But, basically in this course we have tried to cover different parts of these levels, from here, from the acquisition of the image and basic pixel processing and operations, going up to edges, more elaborated shapes like lines, circles, some kind of things that allows you to define objects, and then the scenes. And so we covered this part in previous lectures, segmentation, and now we are going to talk about features and points of interest, and will allow us to go further in other lectures to more elaborated and cool things that they are the target in the end, to have some kind of application for identity, activity assessment, tracking, navigation, a lot of different things. They are based on common steps or common, let's say, implementations of algorithms. So now, today we are here. In the following week we will go further with some applications. So let's first talk about a little bit about invariance of features. So one idea behind features would be to see if two images belong to the same scene. I mean, is this the same thing or monument, like the one that you see here, taken from different perspectives, different moments in time, with different illumination, different camera, different points of view? Are we able to say, based on some processing, that it's the same place? Or even harder? Are we able to know if this picture is taken here? I've seen some presentations in conferences where they try to say, taking images, the city where this photo has been taken, based on, well, of course, landmarks of the city. If the picture is taken in a landmark, then automatically you are able to say the city where it has been taken. When you have many times between the two images. Have you heard about this case that appeared in National Geographic some years ago?
Yes, we
did. What?
Yes, we did.
Of course. And you probably know John Dowman. Do you know him?
Not by papers, by person.
By person, you have known. It's a guy in very famous guy doing iris recognition. This is a famous photo of National Geographic that appeared in the 80s, I think, in the cover of National Geographic. And years later, they found the same person based on the analysis of the iris. This is the story, based on the iris pattern. They were able to say that it's the same person. And then they put this cover in National Geographic many years later. But the idea is different pictures taken at different moments in time. How you can say that to the same person, or the same person in the same scene, whichever, or even harder. You take photos from planes or satellites or something, and then you will have to merge or say that they are from the same place. You can see some points. This is a real experiment. This image taken from one satellite, and other image where they were matched to say that it's this region, this region here, based on seed features, which we are going to explain today. So the idea of invariant features is to find a descriptor or a representation that is invariant to different transformations that you can find in the image. Rotation, different points of view, which is 3D rotation, scale, lightning. Of course, the more perturbations that you have, the stronger the features need to be. And there is always a limit, as we will see later. So the ideal world is that we should be able to compare images with a lot of perturbations between one image and the other. So this is a non-exhaustive list of sources of variance, I should say, not invariance. We could have geometric changes in the image, depending on how it has been taken at different distances, or you have translation or 3D rotation. But there can also be changes in the photometric characteristics, in the illumination of the image, in the contrast, image noise, and there are a lot of factors not related with these two ones, but contributing to changes in these ones. The hour, the weather, if you are outdoor or indoor, the type of sensor, you change your sensor, you get completely new characteristics in the image. This is a more complete list. This is from my PhD thesis, because I did my PhD on biometric quality. But the idea is the same. You get your signal perturbed by different factors, depending on your application. There are a lot of things that can have impact on the image, so you get two images and they are completely different. Or this applies also to signals in general, 1D signal, 2D, whichever. But there are a lot of different factors related with the person itself. People gets older, so your behavior changes. So how you interact with the machine changes. If you are able to use machines or not, you are having old people, the behavior will be different. You have young people that are able to use machines, so the interaction with the system changes. These are factors that should be taken into account. For the environment, the operation of the system, if the user is familiar or not, how the sensor is used, how time passes between different acquisitions, a lot of things. The sensor itself also has impact. You change your sensor, you have a better or worse sensor. You are comparing signals coming from different sensors. This is a problem in itself. You take a picture with one camera and other camera, and you see them, say, okay, there is difference here. Do I have features that can be used too much? And also the inner of the system. If you are applying compression or other things. So more motivation. We need features for a lot of tasks that are here. So great news, we are nearly there. We are nearly able to do some cool stuff. So what makes a good feature? Well, local features. The concept between local features is that you want to find points of interest in your image based on some property around the point. You want to get points in your image that they are unique in some sense, like there is on a later slide. But the idea is that you have different points, then you extract a vector in these different points that summarize some kind of property around it. This is the concept behind local features. And then you use this vector for classification, recognition, whichever comes later. And also you can track these features over time, your video, if you have video information. This is an example of points extracted in an image using a shift algorithm, I think we will see later. And there is also an idea with features. You can have different scales in your image. And this is represented by these circles here. We will see later. But what is mostly done is that these points are extracted at different scales of the image. So depending on the scale that you are using, you are analyzing a bigger or a smaller neighborhood when you extract these features. I hope that it will be clear later. I'm not being quite clear now. And this is an example of feature extracted using different algorithms. Shift, that we are going to explain today, but there are many other algorithms that are implemented in OpenCV, the 4 of them. And each one has a different feature extraction method, point detection for feature extraction. So you see that the points are somewhat different, they are not the same. But the idea is that you find points that you think are relevant in your image, and then you extract features around. So we want points that have some kind of uniqueness around. Regions that are unusual. For example, if I say you, okay, mark points here in this image that you can use later in this image to say that they are the same. How would you do that in this case? Would you mark this point here? Or this point here? I mean, I give you this image, say mark points in the image, and then come back later, have this image, and mark the same points, so you can align them or merge to say that they are the same image. You probably would mark this point here or this point here.
Center, to get rid of the stretching, then it should be center. If I mark the corners, then if it stretches or scales or something.
Yeah, well, but if you mark this point here, it's not representing something particular. You could mark whichever part of this region here.
But I could mark it anyway and reference its position with the neighboring positions of the other points.
Here,
yeah,
with respect to?
with respect to the yes.
So you need these points.
Yeah, I
here.
still need them,
But well, the idea behind is that the point should be unique enough
okay.
in the neighborhood. Maybe it's clear here, right? How would you memorize this face? I tell you, okay, look at this face and try to memorize details of the face. So then I put you later the same picture or a different picture and you tell me, okay, it's the same person. Where are you looking at? Here?
No.
Here? Have you looked mostly to the eyes? Or nose or mouth? So the idea is that if you put here and you move from this point, the properties change a lot. If you put here, well, we are in a uniform region. This is not unique, let's say. But these points here are unique in the sense that if you look around and you move, things change a lot. So this is the idea behind, which is a good point for recognition. Not a flat region, but if you move, things doesn't change a lot. If you are in an edge, every point along the edge, if you look around, you think, okay, I'm in the same point. But corners, for example, they are quite significant. Because if you move a little bit from the corner, things change a lot. So this is the idea behind using local features. Finding points that are unique in some sense, so you extract features around, and then you use this point and these features to compare with other images for whichever, recognition, tracking, detection, whichever idea. We saw a corner detector in a previous lecture, and there are algorithms that are making use of this corner detector to extract relevant points in the image. This is one example. We are going to see another example, which is the shift algorithm, because, well, it's the most famous, I would say, feature extraction method that is being used now. It claims to be robust to different image variations. We will see how, scale, rotation, translation, illumination, and so on. And the idea is what I've been told, what I've been telling. You extract points in the image that are unique or relevant, You extract a descriptor around the points, and then you can use these points for matching. At height level, what this method does is to detect points, and to achieve scale invariance, what it's done is to get points at different scales in the image. So you have a new image at a different scale. Since you extract points at different scales in both images, hopefully you will get the same point in one scale and the same point at the same scale in the other. You get the idea? Then you do some elimination of unstable key points, points that are along an edge, of interest, that we have seen before, and points with low contrast, because they are sensitive to noise. And then, to achieve rotation orientation invariance, in each point we get the dominant gradient orientation around, and then we rotate the neighborhood to make it independent of the orientation. And then we extract the properties around, which are based on image gradients. We will see later this is the big picture. And then we have different points extracted from an image. We can use these points for matching with another images.
Well, how would you explain that SIFT are so good? There's like not a single best other feature.
Well, I cannot tell. Just experiments, and I think that it came first. And sometimes when it came first, people start to use it. And then, well, there are other features, but the idea is that it's real time, and it's robust enough for many applications. Maybe it's not good for applications, and then you say, okay, SIF is not working in my case. But it's like face detection. We will see in another lecture. You can detect face based on many things, but one detector came, which is viola ions. It's real time. It's not working very well in all situations, but it's working. So many people now are using viola ions just because real time, available online, and a lot of things. So with SIF is more or less the same. It came at a specific point in time. Then people start to talk, and many methods that have come later are based in the same idea. So you end up referencing SIF. So you get the whole picture. You get points, get information around, and then use those points for matching. So this is how extraction is done in SIF. It's a horrible slide, but I think I'll try to explain. Do you know the idea of the difference of Gaussian space? Have you heard about that before? Have you seen something like that before? So the idea is that you have your original image, and then you apply different Gaussians with different standard deviations here, and then you subtract these images. So when you get the difference of Gaussian image. You remember that from the edge detection lecture? This is for edge detection. Apply Gaussians with increasing signal, subtract the images, the difference of Gaussian images. Then take your original image, divide the scale by 2, reduce the size to half, and then do the same with the same filters. So effectively you are duplicating the sigma of the filters. You are extracting things at a different scale. You are looking at bigger neighborhoods. You remember that? You increase the sigma, you are analyzing a bigger region. And then you repeat this procedure until your image is small enough, so you cannot do it anymore. So you get different images at different scales. And for all these images here, the different of Gaussian images, what you do is to find maxima and minima with respect to this neighborhood in the same image. Imagine that you are here. You find the maxima or minima with respect to these points here, and these points above, and these points below. You have a 3D neighborhood around each pixel, and then you find maxima or minima. You get the idea? Gaussian, different sigma, then different of Gaussian, then maxima or minima detection in the 3D neighborhood, represented by these images here.
What is the difference of Gaussian gives you?
Why do they use?
Why difference of Gaussian?
Oh, do you remember what we had in different of
They
Gaussian?
give you the edges.
These edges.
And if you want to detect corners,
So you are doing detection here in the edge image. Different of Gaussian is fast to compute. If you remember, you are doing Laplacian. which is second order derivative, but by doing different of Gaussian, you are doing it faster. You don't need second order derivatives. You only need Gaussian filtering, which is quite fast. And at different sigmas, you remember if your sigma is small, you get detailed edges here, but when you increase sigma, your small edges disappear, and you only get edges of a bigger size. But you are detecting all of them, because you are changing the scale of your image. So you are getting, in theory, edges in all possible scales, until your image is small enough. So this is the idea behind them. These are the parameters that are used. You usually have here 5 Gaussian images, and 4, no, 5. Here. These are the exact values of shift based on the optimization that the author of the method did in the paper. You can find these details in the shift paper, but the idea is that reducing the image and finding points in the different of Gaussian. And then you get a lot of points in your image. And this circle here is representing the scale where it has been detected. Effectively, the sigma of your Gaussian. Because if you detect the point in the original image here, you are applying, let's say, a Gaussian with this standard deviation. If you reduce the size to half, then your Gaussian is covering a bigger region in the original image, and then if you reduce the scale once more, the point that you detect here is based on applying a Gaussian to this neighborhood here. Because your Gaussian never changes. What it changes is your image that is reduced. So each time you reduce the image, your Gaussian is covering a bigger region. So this is what is represented here by these circles of different sizes. The scale where you have detected the point. Clear?
So the smaller the circle is, the smaller the image was when I found the point.
The bigger. That's the other.
Yeah.
You apply your Gaussian here. When you reduce, effectively you are increasing the size of your Gaussian is covered. So this circle here is a point detected with a smaller image. Then there is elimination of unstable points based on 2 thresholds. One is elimination based on the absolute value in this different Gaussian image to eliminate low contrast points, because these points are sensitive to noise. You have noise in the image, and maybe you don't detect this point anymore, so you are not interested in this kind of point. And also points that are along an edge, because they are not discriminated. You are using edge images to detect points, but then you don't want points that are exactly on a flat edge. And the concept is we saw in a previous class, is analyzing the alien vectors and alien values in the point. There is a formula in the book based on the use of the Halmstad metric. So if you have large alien values in both directions of the gradient, then you have a corner. And you need a threshold here in your method. So there are two thresholds in this method that should be fixed. In the paper, the author gives an idea of which threshold to use, but maybe you implement your method and you see that you may not have enough points, or you have too many points. So maybe you have to modify these thresholds. In fact, I did experiments with that for iris recognition. I will put you an image later, and we found that we got too few points. So we had to reduce these thresholds to get more points. So you have to play with them. So now that we have points, we are going to analyze the neighborhood around this point, right? First of all, what it's done is to detect the predominant orientation around this point here, based on the gradient. So the gradient then is extracted from the image. In this method, they are using a very simple gradient extraction method based on the points around the neighborhood, not advanced edge detection, nothing, just different between gray values around. So imagine that this is the point that we have detected, and this is the neighborhood around, the different pixels around. This is representing the orientation based on the gradient, and the strength, the magnitude of the gradient. The length of the arrow is representing the magnitude. So then, with this, we can build an histogram of directions. Each point here, we increase by the magnitude the point of the histogram that belongs to this orientation. So then we get here a peak telling the predominant orientation of the edges around the point. This orientation, in theory, is, how to say, if you rotate your image, your predominant orientation changes. You want to be invariant to that. So you compute this predominant orientation and then rotate your region of analysis. You rotate the image back if you prefer. What we are going to do is to extract features with respect to the predominant orientation. So if you get this image rotated, you detect this point, then you will rotate your window accordingly. So in each case, you are going to analyze the neighborhood in the same orientation. The neighborhood is analyzed in the same way as before, but using a different concept. This is your point. This is the gradient around, and then what it's done is that it's divided in boxes here around the point, and the histogram is done for each box separately. This is 2 by 2, but the algorithm uses 4 by 4. This is what it's exactly doing. This is the point that we have detected. We look into a neighborhood of 16 times 16, yeah. And then you divide in different boxes, 4 by 4. And for each box here, we compute the histogram orientations. And this time, the orientation, the histogram is quantized, I think. Yeah, it's quantized into 8 orientation bins only. So in each window you get 8 values corresponding to the 8 orientations. And then we put all together into a vector.
So what you do is you find your points, you look at the neighborhood, you rotate the point to a known orientation, and then you take the other orientations of subparts. That's your features.
Okay. This is the feature vector. And then you put together 4 times 4 bins times 8 orientations. This is your feature vector in each point. So you are analyzing orientations in more elaborate way. So this is the concept behind it. In this case, this point has been detected in this scale. So you are obtaining this histogram on this region only. In this point has been detected at another scale. You are analyzing a bigger region here. But if you have a new image at a different scale, you will extract the feature accordingly to the scale. So hopefully, if you get this feature in a different scale of the image, they should be the same, because you will adapt your neighborhood accordingly to the scale where you have detected the point. So this is how this method gets scale invariance. You extract the same feature in the neighborhood with the size adapted to the scale. And this represents the predominant orientation. So if this is the predominant orientation here, then you extract in this way, and then you concatenate always in the same order. So if you rotate the image, you will rotate your window, and you will concatenate the vector in the same way always. So the feature vector should be equal. So you have the complete idea in mind? So then it's time to match. You can match based on the Euclidean distance. You have a vector of integral values, which is the number of times that orientation happens in the neighborhood. So you just use the Euclidean distance. And then if you have two different images with different points, you start to analyze. You get one point, find the closest point in the other image, and you do the same for all the points here. But there is a criteria that you can apply. That is, get the closest point in the other image, and get the second closest point here. And if the ratio of these two distances is sufficiently small, then you say, okay, these 2 points are the same in the two images. Okay? And you repeat this for all the points here. So,
how is it real time? Because CPU is usually working when there are like million of key points.
yeah, it works quite fast. I mean, I've used an implementation in MATLAB based on, well, it's written in C below. It's working quite fast. Well, depends on the size of your image also. If you use, I'm using 600 times 500 or something, and well, it's few seconds in MATLAB. So if you implement in dedicated hardware, it should be fast. Well, let's see in mobile telephones. I mean, I'm not testing in Android or similar. I'm talking when this appeared with PCs. There is another possibility of matching, which is written in the book. Instead of trying to find these individual matches, you try to estimate a transformation between the two constellations of points iteratively by adding and removing points each time until your transformation converge in some way, and then you get the number of points that you are using in your estimation as a measure of how many points are in common between the two images. Right? In different ways of finding matches between two images. So what you get finally is two images and how many points they have in common, or where the points of this image are here. And no matter the scale where you get this point, because as I said before, in this case you extract features here, and in this case you will extract features of smaller window. So finally you are covering the same region. So hopefully the feature vector is equal. And of course, since we rotate this to the predominant orientation, we get a rotation invariance. And translation invariance because we allow the point to be detected in any region of the image. Okay?
I'm sorry, I missed that. The Gaussian is same for the whole image, the
Yeah.
size of the Gaussian.
Yeah. You apply the same
both
Gaussians to different versions.
To every point the same Gaussian, and to every image the same Gaussian, same size of the Gaussian.
Yeah. Then you reduce the image and use the same Gaussians.
But you use multiple Gaussians.
Yeah. Of
So
different.
you get difference of Gaussian images.
Yeah, because there's one feature vector. So it's not like there's a different feature vectors for both images. It's
Yeah.
okay.
So now there are many ways of using this. One way, well, I prefer this one first. For instance, you have this object here, and you want to detect in an image. So this is like your training image. This is your object only. You extract points here and find in this image if there are enough points that are matched with the points extracted here. So you use different training images to find, to see if the points that you extract are found in a random image. If you get many points here matched in another image, you say, okay, I can presume that this object is present here. Get the idea? But there is another case, which is identity. We use this method for identity. And in this case, okay, you can have one eye image and extract the points from this image for what? To find eyes in another images. But in this case, what we wanted to say is the identity of this person the same of this person in this image? So the idea is different. It's not detecting things that looks like an eye, but it's discriminating between different eyes. Okay? So in this case, your training image is an image of the person that you want to recognize, not a lot of different images of eyes. Okay? The concept is different. Recognizing an object, so finding what makes similar to different images. You can have different eyes, and you want to find eyes in an image, so you want to find what makes similar all these images. But you can have eyes of different persons, and you want to separate what makes different two eyes or two images of an eye. So in this case, what we did is to segment this region here. It's not shown here, but you see that the points are only extracted in the iris region. So then you have two images, find the matches, and if you have a high percentage of points that are matched, you say they are from the same person, these two images. If you don't have many matches, you get 50 points in one image, 45 points in the other, and you only get 5% of the points matched, you say, okay, these images are not from the same person.
Okay. So you only compare the number of matched,
Yeah.
not whether the positions of the matched points. I mean, there should be a correlation between where you find a point in the left image, and if you match it to a point in the right image, it should be at approximately the same position.
Well, yes, well, this is achieved with the matching procedure. Okay. In this case, we applied a removal step, is not shown here. We got some points doing diagonal thing, and then we removed points which were not having the predominant orientation. In theory, all your lines should be parallel. Well, not they are, if you have
Yeah.
different scales, you have some kind of triangle, but they should be parallel. So you can use this information to remove false matches. This is
Do you store the predominant orientation of the block you matched in the beginning inside the feature vector as well?
They are removed. You just get the predominant orientation, extract your feature vector, and then you remove this information. You assume that it is extracted based on the predominant orientation. Of course, you could extort and use this information.
Because then you need to make sure that the images are rotated the same way.
Yeah. It's not used by the algorithm,
Mm.
but it could improve, of course. This is. Sorry?
What movie was this one? Taken from some
Groundhog Day or something.
I don't know.
He's traveling some elephant, I think, right?
No, it's the one where he says living the same day all over again. He's making same mistakes unless he's doing the day perfect.
I don't know if it's in the book, but it's not mentioned.
It's a Groundhog Day. Yeah.
Okay. So that's the idea. You get an image for training and see if it appears in other images based on how many points are matched. You need a threshold also to say, okay, I am sure enough that it's the same object or not. You can also use for image alignment. Once you get the correspondences, then you can apply alignment algorithms based on these points. There are algorithms for that. With Shift, you provide the algorithm with the points that are common in the two images. Of course, you have, it's not rigid, the transformation. You have, especially if you have 3D rotation, it's not perfectly just rotate and translate.
And then the lines are not parallel anymore.
Yeah, but the algorithm can help for alignment. There is a nice application. You go to this link here that you can have different sub-images. This is pretty much that what it's done with Blue Mobile now, that you can have a panorama image. Have you tried this with Blue Mobile?
Done this.
So you have different images that you know that they form a mosaic or something. So they should overlap, of course. So you can find overlapping between the different images. Put here, apply deformation. You have here squares
And then you smooth the
smooth.
vertices.
So do any improvement in the image processing of the data. You use this algorithm for alignment. There are many other local features. She's the owner. Do you remember these patterns? Of course, there is some uniqueness if you put here, if you move, then things change a lot. This is the concept of local features. Not this pattern. This pattern is edgy, but so of course this can be used for extracting features. And this has been done by Anna in her thesis using these patterns to extract image properties around points, selected points. You are using fingerprints, right? So you use bifurcations and endings in fingerprints, and then you look at find how many of these symmetries are around. So there is in the book, in one of the books, there is an experiment that they have tested 4 different features, 3 different features, of course, against different deformations. One is rotation in steps of 1 degree. There is change in scale, change in brightness by adding or subtracting 1 to all pixels in the image, and then Gaussian noise. This is Gaussian, an example of Gaussian loop. And this is adding values to the brightness, but you start to get saturated image. So you start to have this effect. These are the results with rotation. We have only explained shift. Well, maybe one reason is in this comparison shift is more or less the best in all different cases, as we will see here. In rotation, what they have done is to get points in the original image, get points in each of the rotated images, and find how many points you have matched between 0 and 100%. So as you rotate the image, you get between 20 and 60% of the points matched on using exactly the same image, but only rotated. So well, it's rotation invariant to some degree.
It's interesting to see that the red line has its maximum at 90, 180 to 170 degrees.
Yeah. And this is when the image is completely...
Which is pretty weird, because the histograms of gradients should be invariant. I don't know.
Well, maybe it depends on how do you interpolate your image when you rotate.
Yeah, if you do a 90 or 180 degree, you have a one-to-one mapping of pixels.
Yeah, 180 is just exact mapping, but
for 92 actually.
You have to apply interpolation. This is for scale. But this is scale 1. You can see, well, you still have 80% here with some scale, but
it's a bit surprising that the others don't get to 100%.
Yeah, yeah. Yeah, I didn't check it out.
I give you two of the same images. No, these are not the same.
Yeah, 80%.
Yeah, there must be, or maybe, well, they maybe are not using the same image. They're only using the next and the previous. So they should have interpolated it.
Yeah.
Well, if you have a bigger image, of course you don't miss information, and you still get 80% of the point. But if you reduce the size of your image, you lose information. There is a limit in how small you can go. This is for brightness variation. It's the same. Well, this is more tolerant, but in some point you start to get the saturation in your image. Things go down. And this is for blurring. It's the same. If you apply blurring, you start to get to loose edges in your image.
Their stiffness bad.
Yeah, in this case it's bad. You may have to consider some kind of image enhancement. So this is another field. But depending on your application, if you have different levels of blur, then you have to consider. And then let's pass time here. I will try to go fast. So the idea behind textual feature is that there are patterns that are not characterized by points, but by regular repetitions. In this case here, if you move from one point to the other and look around, you see more or less the same. Right? Here, if you move, things change, but here, precisely what you have is repetition of properties. But you are still interested in these properties. And maybe you don't have a dominant direction. here. So for that, there are other examples here. They are characterized by the whole region, not only one point. So it's the two versions: point and things that change around, or exactly the opposite, big region with common properties. So it depends on what you are interested in.
Why would people want to look into the grass?
Well, satellite images or agricultural images. This automatized growing machines that they put the seed in the ground, but if they find I don't know, bad seeds or something, they just move, or they just take it out and put the seed or something. We had a presentation here some time ago where they put cameras in agricultural machinery, and then they put the seed at constant, or maybe it was to remove bad seeds instead in there. So this should be able to discriminate between bad seeds and good seeds. And then when you have a bad seed, take it out. So one kind of feature is GLCM. Are you familiar with GLCM? Have you heard before? It's what you do is you take your image and you build a matrix here. In this case it's 8 by 8. And what you do is to quantize the gray values in your image to 8 levels in this case. You can use 8 or 16. So you quantize the gray values in your image to 8, for instance. And then you take one pixel in the image and look to the neighbor. And in this case, if they have the same gray value, you increase 1 in the position. Well, it has the gray value 1, and here it has the gray value 1. So you increase 1 in the position 1, 1 of your matrix. Here, this has value 1, and this has value 2. So you increase 1 in position 1, 2 of the matrix. So this is encoding the joint probability of gray values between neighbors in your image. So you repeat this for your whole image, for your whole region of interest, and you get a matrix of probabilities of having joint pixels having this different combination of gray values.
Is this working well with noise?
What?
Is this working well with noisy images?
Well, I think so.
Okay.
Well, it depends on your images also. If you have noise, you may can't enhance your image. So after you get this matrix, yeah, please go ahead. After you have this matrix, you can extract different properties. These values here represent probabilities of joint gray values. So you can extract different properties from your image based on these probabilities and the position in the matrix. In this case, for instance, you can have these measures here, which are contrast measures, because you have the difference between the positions here in the matrix. Distance is diagonal. Points in the diagonal mean pixels are added together and have the same gray value. So the contrast is small, and as you go far away from the diagonal, you are having pixels, neighbor pixels with high difference. And this is represented here by A minus B. You can have other measures of regularity where you only use the probability here. And you also can have, of course, statistical properties, mean, standard deviation, different correlation values. So then, what you can do, you have your image, you extract whichever properties you want, and then you train a classifier. If you have new images, then you classify against your training set. Let's see some examples of that. We train that, for example, to discriminate between real and fake eye images. This is images acquired with a camera. This is the real image in front of the camera, and this is the image printed on a piece of paper and put in front of the camera. And we did the same with infrared images. This is the original image with an infrared sensor, and this is the image printed and presented to the sensor. So then we extracted some GLCM features from the real ones and some GLCM features from the fake ones, trained a classifier, an SVM, and then you put a new image that you have not seen before, and then extract the same GLCM features and apply a classifier to say it's real, it is fake. And it's based on the texture of the whole image, not in points of the image. This is for a master project that we have here also, where we used these features to detect fallen people or common objects that you can find at home. This was for old people, I think, that are in the living room, so you can have cushions or you can have a sofa or whichever, and then have a fallen person. So we took some images of fallen people, took some images of common objects. This was done with a Kinect, so we have the depth image. We can segment this region based on the depth information, and then you extract GLCM features from your region of interest and trying to classify human people fallen on the ground or objects, and then you say if it's a person and it's not a person. And ideally the robot is able to approximate, and if it's a person doing something, triggering some alarm. The next kind of textual feature are Gabor filters. Have you heard about Gabor filters before? These are filters which are the multiplication of Gaussian with a sinusoid. In the sinusoid you have the frequency, and in the Gaussian you have the signal. So the product looks like that. You have here the oscillation of the sinusoid at the frequency that you have defined, and the envelope of the Gaussian. So you can rotate your sinusoid. You can decide in which direction you have your oscillation, and you also define the size of the neighborhood that you are analyzing. So you are analyzing different frequencies at different orientations. And you can have the cosine or the sine part. There are two versions. The cosine part is even with respect to the origin, and the sine part is uneven. Sometimes they are used together and in a complex way. So you have cosine part plus I multiplied by the sine part. You have a complex with them. Or sometimes they are used separately. For instance, in fingerprints, we will see an example, they are used separately. So if you apply a Gabor filter to this image with different orientations and you set the frequency to this distance here, you get different images with the different regions of the image having the orientation of the filter. Here you apply the filter with vertical orientation. You rotate the filter a little bit, so you get here marked or amplified the regions of the image having the orientation and the frequency of the filter. So in this case, they divided the image in different cells, and for each cell they compute the variance of the gray level here. In this region here, where the orientation of your edges is not the same as the filter, the gray value here is more or less constant, so the variance is small. But in regions where the orientation is the same as the filter, you get high variance here. So you can see here in these images how the different orientation regions are marked using this feature. And if you extract this vector from different fingerprint images, you can just directly compare using Euclidean distance. You concatenate this into a vector, for example, and then you can compare different images. So this is for a constant frequency, but of course you can vary frequency and orientation. So you have filters with different orientation and different frequencies. Effectively, you are sampling the spectrum. Here, you move in the frequency value and in the orientation. So if you change the frequency and the orientation, what you are doing is sampling or getting, let's say, the average of each part of the spectrum. If you reduce this sampling to the infinite, you will get exactly the spectrum. Have this idea? Depending on how many different frequencies and how many different orientations you are using, you are sampling the spectrum at different resolutions. If you push it to the infinite, you are exactly sampling each point of the spectrum, ideally. So this is a way of roughly sampling the spectrum and analyzing different parts. This is another example that where we apply this for recognizing people. We apply different couple filters in different points of this image. So for each point, we get different sampling of the spectrum, then we put together in a vector, and when we have another image of a different eye, we get the same vector and find the distance between the two vectors. So this is not, we are extracting a vector in different points, but these points are not selected by any particular feature around. They are just put here constantly. So we are analyzing the texture around these points. This is the idea of textural features. And the last one is the LBPs, very fast, only 2 slides. This is also a very discriminative and famous textural feature proposed some years ago, but now it's been widely used. And the idea is that you put in a pixel, you position yourself in a pixel, and look around the 8 neighbors, and then find the difference of gray values here between this pixel and the 8 pixels. If this pixel is bigger than these pixels here, well, you get the difference between this and all these 8 pixels here. If the difference is negative, you put 0, and if the difference is positive, you put 1. So you get a binary vector here, based on the relative difference between the center and each member here. And then you build a vector, like this one, of 2 to the power of 8. You have 8 different pixels here, so this vector can have 2 to the power of 8 different values. And then you do the same for each pixel of the image. And then you can get that feature vector for the whole image.
The grayscale image.
Yeah. And or you can do it in different ways. Okay, you get, sorry, and you get the histogram. Don't concatenate all pixels. You get the histogram of values of all the pixels of your image. For instance, it's used in face recognition, but it's used applied to windows. So you get the LVP histogram in each window, and then concatenate the histogram of all the windows. You get a big feature vector for the face, and then half new face, just compare the feature vectors. And of course, you can use textures for segmentation, as I said in the previous part of the class. If you know that your regions have different textural properties, you can apply a texture detector. So each region will have a different value of texture. So it's like having gray values in your image. You can use a segmentator based on gray values, using the values of the texture property of your image, let's say that way. You get this idea? Maybe I'm going too fast. No, it's okay. Okay, so if you segment based on gray values, you can have gray values using texture values. So this is all I wanted to cover here. And this is the references where you can read more. Basically these two books, but I will put additional references in the web of the different methods that I have presented. I will let you know when it's on.